Hello students, today's lesson is on sinusoidal curves. The word sinusoidal simply refers to functions that are waves, like the sine and cosine wave, and any transformations of them. We will review 8 different transformations, including vertical shifts, horizontal shifts, reflections about either axis, and vertical and horizontal stretching. Let's take a look at the graph of y equals sine of x. This is one parent sinusoidal curve. It begins at the origin, reaches a max at pi halves comma 1, gets back to the x-axis when x is pi, reaches a minimum when x is 3 pi halves, and that minimum is negative 1, and then gets back to the x-axis and completes one cycle by the time x is 2 pi. So one cycle is completed between x equals 0 and x equals 2 pi. That horizontal gap is 2 pi units, so the period is 2 pi. And the wave goes as high as 1 unit above the x-axis and 1 unit below the x-axis, so we say the amplitude is 1. Now the x-axis we call the midline. This is the line about which this sinusoidal curve is oscillating. Now one kind of transformation are vertical shifts. If I take this graph and shift it up 1 unit, notice the midline is now at y equals 1. The maximum is now at a height 2, but that's only 1 unit above the midline, and the minimum, which is at a height 0, is only 1 unit below the midline, so the amplitude is not changed. The amplitude is still 1, and the period is still 2 pi. So you can shift vertically up or down, and none of these vertical shifts have a change in period or amplitude. We can also shift horizontally. If I take the sine wave and shift it right 1 unit, track where the origin goes, this shift also does not change the amplitude. We still go 1 unit above and below the midline, nor does it change the period. It still takes 2 pi x units to complete one cycle. This decimal you're seeing here is 1 plus 2 pi. We can also reflect the graph around the x-axis. To make this graph, the red was the original and the black is the reflected graph. We can also reflect across the y-axis. Now the origin will not move anywhere, but these 4 points over here will reflect to the other side of the y-axis. We will not use reflections around the y-axis very often in this lesson. You can also stretch vertically. Notice these vertical stretches change the amplitude but do not change the period. If I want the new amplitude to be 2, then I do a vertical stretch by a factor of 2. If I want the amplitude to be 1/2, then I do a vertical stretch by a factor of 1/2. Sometimes I call this a vertical compression because relative to the original graph in red, the graph has been compressed toward the x-axis. And I can also do horizontal stretching and compression. Horizontal stretching, horizontal compression. Notice the heights of the maximums and minimums do not change, but the x-coordinates for their locations do change. So if I want to compress this horizontally so that the period is now pi, then I would need to do a horizontal compression by a factor of 1/2. So now we complete one cycle by the time x is increased from 0 to just pi. So the period is now pi. The amplitude, though, is still 1. And if I want the new period to be 4 pi, I need to do a horizontal stretch by a factor of 2. So now beginning with the origin, we have to go to the right 4 pi units to complete one cycle. But notice the amplitude is still 1. All right, back to our notes. The first one, vertical shift, up k units. You simply add k at the end of the rule, and we are assuming k is a positive number. So you take any function and add k to it at the end, and you will have a vertical shift, up k units. So in the case of sine of x, you would begin by just writing your parent function, and if you wanted to shift up 3, then you simply add 3 after the fact. So let's open up new Desmos, type in y equals sine of x, change the color to black, zoom in a little bit. Notice the x-axis is marked by whole numbers. If you want them to be increments of pi, then click the wrench and x-axis step, type in pi for pi, and notice what it shows us. Or you can force increments of pi halves. If I put plus 3 at the end of this, the whole graph will be shifted up 3 units. If you put plus k and add a slider for k and let k vary from 0 to 3, drag k to 0, change the animation property so it goes through once, and then hit play, and you'll see the graph transform dynamically and stop when the vertical shift is complete. All right, back to our notes. If you want to shift down 1 unit, then you begin with sine of x, and you simply remove 1. Again, these are examples of vertical shifts. Now, if you want to shift right 2 units, then you take your parent function and you replace all x's with x minus k. That might feel counterintuitive. So to shift right 2 units, you begin with sine of x, but then you replace x. Now, when you do this, I recommend you erase the x and in its place put parentheses. This is the position of the argument. the argument used to be x, and now we want it to be x minus 2. This is different than saying sine of x and then minus 2. Without parentheses, the order of operations would be to do sine of x first, and then do this minus 2 at the end, and that would be a vertical shift down 2. But with the parentheses, our order of operations is to remove 2 from x first to make a new argument, and then do sine of that new argument. And this will have the effect of shifting right 2 units. So we have our parent graph, delete the x, put in parentheses, and in those parentheses type in x minus 2. And notice this location right here. This used to be the point that was going through the origin, but it's been shifted to the right 2, and every point of this graph has been shifted to the right 2. And if you want to animate this, put a k here, add a slider, put the bounds from 0 to 2, make this play only once, drag k to 0. Here's the parent graph, and when you hit play, you'll see it shift dynamically to the right 2 units. If you want to see whole numbers on your x-axis, go to the wrench and get rid of the step size. It'll default the whole numbers, and you can clearly see one cycle of the wave beginning now at 2, 0 instead of the origin, and then doing one cycle and completing one cycle 2 pi units later. Right, back to our notes. If you want to shift left by any amount, then replace x with x plus k. So in this case here, if we want to shift left 0.5 pi units, then begin with sine of x, erase the x, replace it with parentheses, and in those parentheses, write x plus 0.5 is the same thing as 1/2 of pi, which is the same thing as just pi halves. So we could just say x plus pi halves. When you take a sinusoidal curve and shift it left or right, then these are also called phase shifts or horizontal shifts. Now to reflect any graph across the x-axis, you multiply the rule of that function by -1. So here's the rule for the sine function. If you multiply it by -1 or simply put a negative in front, this will have the effect of reflecting across the x-axis. Now if you take the sine wave and you want to reflect across the y-axis, well, to reflect any graph across the y-axis, you replace all the x's with -x. So in this case here, we would replace the x with -x. Now in the case of sine of x, if you take this graph and reflect it across the x-axis, you put a negative in front. Y equals negative sine x. So the black graph is the parent, the red graph is the reflection across the x-axis. But if you take the sine wave and reflect it across the y-axis, we'll type in y equals sine of parentheses and put -x, change that color to orange. We get a graph that looks exactly like the reflection across the x-axis. The red is the reflection across the x-axis, and the orange is the reflection across the y-axis, and they're the same. So the sine of -x and the negative sine of x are equal. And this is because sine is an odd function. Now in the case of cosine of x, if you reflect cosine of x across the x-axis, that means you put a negative in front of it, you get this red graph. It's different from the black graph. But if you take the cosine graph and do a reflection across the y-axis by changing x to -x, you get the original graph. So the original graph is cosine of x, reflected across the y-axis, it looks no different. That's because cosine of x is already symmetric across the y-axis, so such a reflection has no effect. So cosine of -x is the same thing as cosine of x. And that's because cosine is an even function. In the first case, reflecting sine across the y-axis produces the same graph as reflecting sine across the x-axis. We really don't have to worry about doing reflections across the y-axis. We can limit ourselves to reflections across the x-axis. And cosine of x reflected across the y-axis has no effect on its graph. So for these reasons, we won't do a whole lot of this reflection in this lecture. Now to change the amplitude, we want to do a vertical stretch. If you want to do a vertical stretch by a factor of k, then you simply multiply the rule by k. So you do k times the function. So if you want to change the amplitude to 1.5, then we need to do a vertical stretch by a factor of 1.5. So we begin with sine of x and multiply by 1.5. And we have now a vertically stretched sine wave that goes as high as 1.5 units above the midline and as low as 1.5 units below the midline. So the new amplitude is 1.5. If you want to animate the stretching, then change 1.5 to k, add a slider for k, change its limits from 1 to 1.5, because when k is 1, there would be no change. Select play once, hit play, and you'll see the vertical stretching happen dynamically. It'll stop by the time we've stretched vertically by a factor of 1.5. So vertical stretches will be the way that you change amplitudes, but vertical stretches do not change period. To change the period, we'll need to do a horizontal stretch. And this one has an idea that you have to be careful about. If you replace x with kx, then the horizontal stretch is by a factor of the reciprocal of k. Now normally the sine wave has a period of 2 pi. So if I take the sine wave, sine of x, and I want to do a period change, then you need to replace the x with a kx. And this will be a horizontal stretch or compression, depending on what k is, by a factor of 1 over k. So this means that the new period, and let's use p for the period will be 1 over k times 2 pi, or in other words, 2 pi over k. This gives us a little formula that will help you determine how to do a horizontal stretch in order to get the period that you're looking for. So for example, if you want the period to be 4 pi, then change p for period to 4 pi and then solve this equation for k. So 4 pi equals 2 pi over k. We'll multiply k to the other side and divide by 4 pi. And then simplify this, the pi's cancel, and the 2 over 4 becomes 1/2. So we need k to be a 1/2. In other words, I need to do sine of 1/2 x. So here's the parent. I'm going to type a new line, y equals sine, and then replace the x with 1/2 x. Notice the red graph completes one cycle by the time we get to x equals 4 pi. Now if k is 1, then we just have the parent graph. So if you want to see a dynamic imagery of this period change the coefficient of x to k, add a slider, but for your bounds, this will be tricky. Let your bounds go from 1/2, which is where we wanted it to be, to 1, which corresponds to no horizontal stretch at all. And then if you want to see the stretch occur, you drag k from 1 back towards 1/2. So again, if you want to change the amplitude of a sinusoidal curve, then you do vertical stretches. And if you want to change the period, you do horizontal stretches. And sometimes you need to do both if you want to change both the period and the amplitude. Okay, let's go to the next page. Plot the graph of the given function without technology. Give the amplitude, period, vertical and phase shifts, domain, and range. Then use technology to confirm your answers. Okay, it is clear that the parent graph is cosine of x. Cosine of x begins at 0, 1, goes through pi halves 0, pi negative 1, 3 pi halves 0, and 2 pi 1. So this black graph is the y equals cosine of x, our parent graph. I'm going to do one transformation at a time. Let's first focus on the effect of this minus sign. Multiplying a function by negative has the effect of reflecting across the x-axis. So y equals negative cosine of x will be in red, and will look like this. Now the next change is we have a 4 in front of the x inside the argument. So x is being changed to 4x, and this is a horizontal stretch. So looking at our table, if you replace x with 4x, then that produces a horizontal stretch by a factor of the reciprocal of 4, so by 1/4. This is a horizontal compression, which will change the period. Furthermore, this formula that we have starred right here for calculating the period, if you know what k is, also applies to starting with cosine as your parent function. So sine or cosine of kx will have a new period that can be calculated by doing 2 pi divided by k. So here we know that the period of this wave will be 2 pi divided by whatever k is, and k happens to be 4. Simplifying this, 2 pi divided by 4 becomes just pi halves. So the green graph will look like the red graph, but the period will now be pi halves instead of 2 pi. This horizontal compression will not change the height of this point or the height of this point. This point on the y-axis will not be moved by this horizontal compression, but this point will now be 1/4 as far from the y-axis. So it'll now be here at pi halves comma negative 1. So I now expect one complete wave by the time I connect these two green dots. Halfway between that is when we're going to have our maximum, and that's going to be at pi fourths. Half of that is pi eighths. This is where we'll have an x-intercept. And then halfway between pi fourths and pi halves is 3 pi eighths, and we'll have another x-intercept. And then one cycle of our wave will be this. So the green graph is the result of compressing the red graph horizontally by a factor of 1/4. Notice that the maximum of the green and the maximum of the red is still 1, and the minimum of the green and the minimum of the red is still negative 1. That's not changed. But then the green wave repeats itself. So all my answers now are going to be based off the green graph. The amplitude is still 1, because we only go 1 unit above and below the bin line. The period is now pi halves. We simply use this formula, period is 2 pi divided by k, where k was 4 in this case. The vertical shift, there was none, nor was there a phase shift. The domain will be all real numbers because the green wave goes right and left forever. So we can write that as negative infinity to infinity. And this, of course, is referring to x's. And the range of the green, the lowest y-coordinate of the green graph is negative 1, and the highest is positive 1. So we can say that the y-coordinates have to be in the set from negative 1 to 1, or you can say it this way. Let's confirm with technology. I'll begin with y equals cosine of x, and let's do one change at a time. Y equals negative cosine of x, and then green will be y equals negative cosine of 4x. It starts on the y-axis at 0, -1. At pi 8 it hits 0. At pi 4 it gets its maximum. At 3 pi 8 it gets back to 0. And it completes one cycle by the time we get to pi halves. And then we just get repetition from there. Okay, let's go to the next page. Same instructions. In general, if you see a transformation that is a vertical or a horizontal shift, do those transformations last. The parent graph here is y equals sine of x. Sine of x begins at the origin, reaches a max of 1 when x is pi halves. Notice our change in scale here. Back to 0 when x is pi, a minimum of -1 at 3 pi halves, and back to 0 at 2 pi. And then, of course, this repeats. And here's our parent graph. Let's focus on the effect of the 0.5 in front and make this be red. 0.5 is in fraction form is 1/2. So 1/2 sine of x will be a vertical stretch by a factor of 1/2. I like to call that a vertical compression. So the amplitude will be affected by this. The maximums and minimums will go from 1 and -1 to 1/2 and -1/2. The x-intercepts will not change. So there's one cycle of my new graph. The amplitude is now 1/2. The period is the same. And then, of course, this will repeat. Now let's focus on the effect of the x-halves in the parentheses. So to go from red to green, we keep the 1/2 there, but we simply change x, and x over 2 is the same thing as saying 1/2 x. So my k is 1/2. Well, changing x to 1/2 x is a horizontal stretch or compression by a factor of the reciprocal of k, so by a factor of 2. So this will have the effect of doubling the period. Or we simply use the formula, the period is equal to 2 pi divided by k is 1/2. When you divide by 1/2, you multiply by 2 instead, and so we get the period is now 4 pi. So our green graph will be like the red graph, but stretched horizontally by a factor of 2. So we'll start here at the origin, and need to complete one cycle by the time we get to 4 pi. Let's break this up into quarters. So half of 4 pi is 2 pi. Halfway between 0 and 2 pi is pi, and that's where we're going to have our maximum of 1/2. Halfway between 2 pi and 4 pi is 3 pi. That's where we're going to have our minimum of -1/2. And we draw a much longer wave. And then finally, let's look at the effect of the +1. This is a vertical shift up 1 unit. So take the green graph. So if you focus at the points on the x-axis, they'll now be at a height of 1 unit. And we get this graph here is in orange. Let's label some of the points. 0, 1. It reaches a max when x is pi, and that max is 1/2 unit above the midline. Keep in mind that the vertical shift moved the midline up 1 unit as well. So our maximum is 1/2 unit above the midline, so 1/2 unit above 1. So that's 1.5, or in fraction form, 3/2. Then we have the point 2 pi, 1, and then our minimum is when x is 3 pi, and the minimum is 1/2 unit below 1. So that's 1 minus 1/2, which is just 1/2. And then our final point in one cycle is at 4 pi, 1. So all of my answers now are looking at the orange graph. The amplitude is 1/2. The period is now 4 pi. The vertical shift was up 1. There is no phase shift here. This orange wave does go left and right forever. It continues to repeat. So our domain again is x is any number. So either of these expressions is acceptable for domain. And then the range. The lowest y-coordinate of the orange graph is 1/2, and the highest y-coordinate is 3/2. So our range is 1/2 to 3/2 with brackets to suggest both 1/2 and 3/2 are included in the range. Or you can write it this way. Confirming with technology, here's the parent graph, y equals sine of x. Let's do the amplitude change first to make that red. Now let's change the period by replacing x with 1/2 x. Let me hide the 2 previous steps. Here are 5 points of interest. Notice the period is now 4 pi. And then finally, let's do the shift up. And here is the final graph with 5 key points labeled. Sometimes it's helpful to graph also the midline, so y equals 1, that's the vertical shift. And of course, if you zoom out, you will see that this wave continues forever, forwards and backwards. Okay, let's go to the next page. Same instructions. This time we are doing a transformation of the sine of x. Now notice our scale down here is not in terms of pi. We know that sine of x goes through 0, 0, pi 0, and pi is a little bit past 3, and 2 pi 0, and 2 pi is a little bit past 6. It's about 6.28. Pi halves is approximately here, at which point the sine is a height of 1. 3 pi halves is approximately here, for which x value the sine is -1. So here's our sine wave on this graph. The first transformation is this 2. When you double the sine wave, this is a vertical stretch by a factor of 2, producing a graph that should look like this. Now let's consider the argument. The x has a coefficient, which suggests that there is a horizontal stretch involved, but there's also addition or subtraction with another number, which suggests a horizontal shift. If there is both a horizontal shift and a horizontal stretch, I recommend that you write the argument in the following way. Whatever the coefficient of x is, factor it out of the argument, but leave it in the big set of parentheses to create this structure. So factoring pi out of pi x gives x, and factoring pi out of plus pi gives plus 1. You can confirm that if pi is redistributed across this inner set of parentheses, that you will get this argument here. This is the best way to see the horizontal stretch and the horizontal shift that need to occur as two separate steps. So the first thing we're going to do is we're going to change x to pi x. This will affect the period. Of course, the result would be 2 sine of parentheses pi x. This is a horizontal compression by a factor of 1 over pi, or you can think of that pi being our k value and use the formula that the new period will be equal to 2 pi divided by k. So that'll be 2 pi divided by pi. The pi's will cancel, leaving a period of 2, a whole number. So this point right here needs to be compressed toward the y-axis by a factor of 1 over pi, which will take it to the location of x equals 2. Of course, this point on the y-axis will stay on the y-axis, so we expect a complete cycle in this window from 0 to 2. Well, halfway in between would be another intercept, and then halfway between 0 and 1, at 1/2, we expect our maximum of 2. Keep in mind that we are horizontally compressing the red graph, which will not affect the amplitude of the red graph. Halfway between 1 and 2 is 3/2, at which point the y-coordinate will be -2. And there we have one cycle of the red graph being compressed horizontally, so that its period is now just 2. Then, of course, we can expect this green cycle to repeat in both directions. And then the final change is to change the x to x plus 1. This will correspond to a phase shift left 1 unit. When I do a phase shift, you need to change the x that you see here in more parentheses to x plus or minus a number according to your phase shift. Of course, if you now remove the inner parentheses by distributing the pi, you will see this expression up here. So we're going to shift the green graph left 1 unit. Focus on this point right here and move it left 1 unit. That should move it to this location. And now focus on the orange graph to answer all our questions. We go 2 units above and below the midline, so the amplitude is 2. The period of the orange graph is equal to the period of the green graph, and they both have a period of 2 units. The vertical shift, there is none. We did have a phase shift, though, by going left 1 unit. The domain will be all real numbers. And the range. The lowest the orange graph goes is -2, inclusive, and the highest is +2, inclusive. Here are 2 ways to write that. So I want to draw your attention to this formula here for finding the period. Notice that when k was pi, or some multiple of pi, that when you substitute it into this formula, you get cancellation of pi's, and your period winds up being a number that doesn't involve pi. But in the previous example, our k was a fraction that did not involve pi, so the end result was a simplification that still included pi. Let's do this one with technology real fast. Here's a graph of our parent function, sine of x. We double it, producing a sinusoidal curve that has an amplitude of 2, but the same period. We change x to pi x. That'll change the period to be a period of 2. Now to see this better, I'm going to change my x scale by hitting the wrench and getting rid of this pi halves as my step size. And then I'm going to hide the red and the black. So here you can see the green wave has a period of 2. It completes 1 full cycle between x equals 0 and x equals 2. The final transformation is to shift left 1 unit. If you want to animate that shift, change this 1 to a k, add a slider, let k vary from 0 to 1, make this play once, drag k to 0, and hit play, and you'll see the shift happen dynamically, producing our final result here. Okay, let's go to the next problem. Find rules in both indicated forms for the function that is depicted in the image below. There are 2 forms, here and here. One involves sine, the other involves cosine. We will do this work in tandem with some technology. Let's do the sine one first. Now looking at this image, we can measure the amplitude by first identifying where the midline is. Now the highest point has a y-coordinate of 8, and the lowest points have y-coordinates of -3. We basically want to find the y-coordinate that is halfway between 8 and -3, and one way to do that is to average them. If I do 8 plus -3 and divide by 2, this will give me their average. That gives me 5/2, or 2.5. Thus our midline is at this location. Now from the midline, we would go up a total of 5.5 units, and go down 5.5 units to find my maximum and minimums respectively. This tells us that the amplitude is 5.5. One way to find the period easily is to find how long it takes to go from one minimum to the next minimum. So we go from an x-coordinate of 1 to an x-coordinate of 9. Well, 9 minus 1 is 8. This is your period. The only transformation that can move the location of the midline is a vertical shift. And because our midline is at the height y equals 5/2, we know our vertical shift is up 5/2. Now the plus d right here corresponds to the vertical shift. Thus I know I need a plus 5/2 at the end of my function. This a controls the amplitude, and we need a to be 5.5. We will also see you can use negative 5.5, but let's assume a is positive for now. We're going to focus on this phase shift right here last. Pretend like it's not there, so your argument would just be bx. Well, this b is taking the role of k from our earlier slides, and we know that the period is equal to 2 pi divided by that k, or in this case, b. We also know we want the period to be 8, so this allows us to create an equation where I can solve for b. If I multiply b to the other side, and now divide by 8, we get 2 pi divided by 8, which simplifies to pi fourths. This tells you that we need a pi fourths for this coefficient. Now what I'm going to do is use technology to graph what I have so far, and then identify an appropriate phase shift to get the graph that we actually see in this image. Let's begin with the parent graph y equals sine of x, and make the amplitude change. Now let's do the vertical shift by putting plus 5/2 at the end of this. Now I'll change the period to 8 by replacing x with pi fourths times x. At this point, it's a good idea to change your x scale back to whole numbers by getting rid of that step size. I'm also going to graph the midline, so it's clear that we can see a period of 8 units. We have a peak at the point 2.8. We want that peak to be at the point 5.8. So if I take this graph here and shift it to the right 3 units, that'll move that peak to the correct position. Well, to move a graph to the right 3 units, you replace x with x minus 3. So go back in here where the x is, delete it, put more parentheses, and type in x minus 3. Here are several points now highlighted, and these are the points that match the points in our graph in our notes. So we knew from the technology that a phase shift to the right 3 would produce the desired graph. So our final answer, f of x, is 5.5, which is 11/2, times the sine, parentheses, pi fourths, more parentheses, x minus 3, and then end both sets of parentheses, and then plus 5/2. This was not the only way to do this. Let me remove the phase shift and do a different kind of phase shift. I know I want a peak at the point 5.8. Well, we got there by taking this graph currently, which has a peak at 2.8, and shifting it to the right 3 units. But I could have also focused on this point, 10.8, and shifting the graph left 5 units to get to the point 5.8. To shift a graph left 5 units, I would change x to x plus 5. So next to this x in the inner set of parentheses, put a plus 5. This also accomplishes our goal. Let me get rid of the phase shift. I mentioned earlier that I could have done a negative value for a, which would also include a reflection about the midline. And now I have a peak that's close to 5.8. It's at 6.8. So if I had used a negative 5.5 for my value of a instead of a positive 5.5, I would now have this result, which I would need to shift left only 1 unit. So put a plus 1. And here's a third way that we could have arrived at this graph. In general, you can always use a positive value for a, followed by an appropriate phase shift to get your peaks and valleys to be where they need to be. For that matter, we could have also used a cosine as our parent graph. The values of a, b, and d would not be any different, because we still need an amplitude of 5.5. We still need a period to be 8. So following this series of calculations, that tells us that b itself has to be pi fourths. And we still need a vertical shift up 5/2, so we need plus a 5/2 at the end. The cosine graph begins with a peak on the y-axis. So this point is 0, 1. Let's change the amplitude. Do the vertical shift. I'll graph the new midline. Do the period change by replacing x with pi fourths x. And we currently get to this result. Now I want a peak to be at 5.8. Well, I have a peak at 8.8. So if I take my current graph and shift it left 3 by replacing x with x plus 3, then I can accomplish that. Remove the horizontal shift, and notice I had a peak at 0.8. So if I shift this graph to the right 5, this will also work. So in the inner set of parentheses, put x minus 5. And sure enough, we get a correct final result. Let's put this one in our notes. So g of x is equal to 11/2 times the cosine of pi fourths times more parentheses x, and then we shifted to the right 5, and both sets of parentheses plus 5/2. So here's another way to produce the same graph. Okay, last slide. The temperature during one particular day fluctuated between 50 degrees at 5 a.m. and 80 degrees at 5 p.m. Find a model for the temperature during the 24 hours of that day. Let's assume a sinusoidal curve. We want to make a graph of time versus temperature, where temperature is measured in degrees Fahrenheit. We'll presume that these are Fahrenheit measurements. And now we need to frame a reference for time. If t is 0, we need to establish what time of the day is time 0. For example, if we say time 0 is midnight, so 5 a.m. would correspond to t equals 5 hours. Let time be measured in hours. And 5 p.m. would be when t is 12 hours later, or 17 hours. Of course, you could choose a different frame of reference and say that 5 a.m. is time 0, and 5 p.m. is time 12 hours later. You get to choose. But going with this frame of reference, when t is 5, the temperature was 50 degrees. And this does not need to be to scale. 12 hours later, when t is 17, the temperature reached a maximum of 80. So 12 hours after that, at time 29, or 24 hours after 5 a.m., we expect the temperature to return to 50. And we expect a sinusoidal curve that connects these data points. From here, we want to establish the midline. The midline will be perfectly in between 50 and 80 degrees Fahrenheit. So if you average them, 50 plus 80 is 130, divided by 2 is 65. So 80 degrees is 15 degrees more than 65, and 50 degrees is 15 degrees lower than 65. So we can see that our amplitude is 15 degrees, which means that our value for A needs to be 15. The vertical shift needs to match where the midline is now, which is 65. So D needs to be positive 65. Now let's focus on the period. The period is from 5 a.m. of one day to 5 a.m. of the next day. So our period is 24 hours. This will help us find this value for B, knowing that 24, which is the period, has to be equal to 2 pi divided by B. Multiply by B, divide by 24, and then simplify 2 over 24, so we get pi twelfths is the value for B. Now let's go to technology. Now let's get the amplitude correct. The amplitude is 15. And now let me change my vertical scale. So here's our current graph, a sine wave that goes 15 units above and 15 units below the midline. Now we want the midline to be up at height 65. So I'll zoom out. Let me go ahead and graph the midline, y equals 65. And we need to change the period to a period of 24. So we need to change x to pi twelfths times x. Now let me change my horizontal scale and change my step sizes back to whole numbers. All right, currently we have a maximum at a point 6, 80. But we know we want that to be located at 17, 80. So I would need to move the point 6, 80 to the right 11 units. So where the x is, put it in its own set of inner parentheses and move right 11 units by putting minus 11. And we produce this graph, which you can now use to predict temperatures at other times. So one possible final answer is f of x equals 15 times the sine of pi twelfths times x minus 11, and both parentheses plus 65. And you could rewrite this as 15 times the sine, distribute the pi twelfths. So we get pi twelfths x minus 11 pi twelfths, end parentheses, plus 65. Either of these answers is acceptable. And this concludes our lesson on sinusoidal curves.